Hello everyone, and welcome back to the channel. In today's video, I want to demonstrate a vibe coding within Google Colab, utilizing the power of Gemini AI. Essentially, vibe coding means you guide the process rather than writing the code yourself. You describe the desired task to the large language model, ask it to generate all the code, basically letting the AI handle the heavy lifting of implementation. Throughout this process, if you encounter errors or need clarification, you can simply ask the LLM to debug the code or explain what a specific cell does. Let's explore how this works using a practical example, a competition focused on identifying crop types. We're provided with tabular data and optional satellite imagery, but for simplicity in this demonstration, we will concentrate solely on the tabular data. Credit goes to Mohammed, who shared a very effective approach in a Kaggle notebook. While Kaggle recently introduced an experimental feature to directly connect notebooks to Colab, it wasn't functional at the time of recording. Therefore, I manually uploaded the notebook to Colab. Now that the setup is complete, let's begin. Colab functions as a Jupyter Python notebook, allowing code execution within individual cells. When you select a code cell in Colab, you'll notice several buttons appear. The icon featuring the star represents the integrated Gemini AI Assistant. Clicking this button allows you to interact with the AI. For instance, you can request an explanation of the code within the currently selected cell. This first cell, for example, imports various Python libraries, and Gemini can helpfully break down the purpose of each one. Looking at the explanation, I see common libraries like NumPy and Pandas. However, I'm less acquainted with GeoPandas, which the AI explains is used for working with geospatial data. I've also never used Shapely before. Gemini notes it's useful for geometric operations, including polygon feature extraction. Having this kind of detailed code explanation available with just a single click is incredibly convenient. Continuing on, we execute the next cell to load the data. The output shows we have 953 training samples from 3 distinct classes. Then, we encounter a significant portion of the code for feature creation. Understanding exactly what these features represent can be complex, so this is an ideal place to leverage the AI's explanation capabilities. Let's ask Gemini to clarify this process. Okay, the request has been sent. As expected, the explanation focuses on feature engineering, specifically deriving new features from the geometry data associated with the samples. It seems Gemini often begins its response by repeating the code block itself, which isn't strictly necessary, but we can wait a moment for it to proceed to the actual detailed explanation. Here it comes now. All right, here's the breakdown. The function takes a geodata frame as input. It then iterates through each geometry object within that frame, corresponding to the for loop visible in the code. Inside the loop, it first determines if the geometry is a single polygon or a multi-polygon. Subsequently, it calculates several basic geometric features, including the area, perimeter, and a measure called compactness. This leads us to a very useful capability, asking follow-up questions. For instance, I'm curious about the specific metric compactness. I can just ask, "What is compactness?" The AI then responds promptly by showing the key calculation formula and explaining its meaning. It precisely quantifies how closely the shape of the polygon resembles a perfect circle topologically. That's quite insightful. Oh, that's great. Understanding compactness as a measure of circularity makes sense as a potentially useful feature for distinguishing shapes. I can see how that might be helpful. The code also calculates features related to the convex hull, like its area, and something called moment invariance. Let's dive deeper into that last one. I'll ask Gemini to please elaborate on moment invariance. The explanation starts by describing these crucial numerical features derived from the statistical distribution of pixel intensities, or, in this case, shape coordinates. Breaking it down further, it explicitly mentions central moments accurately calculated relative to the shape's geometric centroid. The truly key insight here is their inherent invariance. These robust features remain entirely constant regardless of the object's rotation, scaling, or translation. Now I understand why moment invariants are valuable. Their robustness to geometric transformations. They roughly capture the shape's mass distribution and variance. Excellent, I learned something useful today through this interaction. This process is proving to be quite effective. It confirms the AI can indeed provide meaningful code explanations. Right, I neglected to run the feature creation cell earlier. Let's execute that now, and the next cell for data splitting. As you can see from the code, it currently implements a simple train test split, allocating 80% of the data for training and the remaining 20% for validation. While this works, a more robust approach would be beneficial. How about we ask the AI to generate code for implementing k-fold cross-validation instead? I almost forgot. I need to phrase this as a prompt for the AI, not just say it aloud. Let's use the Gemini interface. I'll ask, please implement cross-validation and use the F1 score as the evaluation metric. Let's generate that and observe the outcome. It appears the AI intends to use a random forest classifier for this task, which is a reasonable choice. Now, let's examine the generated code and run it to see if it functions correctly. Yes, it seems to be working as intended, outputting the F1 validation score for each fold. This is good, but for the actual competition submission, we need predictions on the unseen test data. A common strategy to improve performance is to train a model on each fold, generate predictions for the test set from each model, and then ensemble these predictions, often by averaging them. Okay, let's ask Gemini to handle that crucial ensembling step automatically now. My request would be something simple like, please predict the test data using the trained model from each fold. Whoops, I did it again, speaking my thoughts instead of carefully typing into the prompt. Let me open the correct prompt window. Also, since this is a challenging multi-class classification problem, simply averaging the raw class labels isn't ideal. For more effective ensembling, especially in multi-class scenarios, working with predicted probabilities is generally better. So I'll refine the prompt. Please predict the probabilities of the test data using the model from each fold. Then, average these probabilities across the folds and determine the final predicted labels for the test data based on the averaged probabilities. Let's try generating code for that. All right, generating the code now. This really highlights the vibe coding concept. You articulate the desired functionality, and the AI attempts to write the code, which hopefully runs correctly. Let's monitor the process and see if the generated code aligns with our request. It seems to be processing fold by fold. Yes, it looks like it's generating predictions and preparing a final submission file just as we asked. Let's run this cell. Excellent, the code executed successfully and generated the ensembled predictions. The final step is to save these predictions into a submission file in the format required by the competition. Conveniently, the original notebook already contained some boilerplate code for saving submissions, which I can adapt or reuse here. Let me go ahead and save the submission file now. Okay, next let's submit the solution and see how it scores on the leaderboard. I think it is pretty good. So that wraps up our demonstration of vibe coding with Gemini in Colab. It proved incredibly helpful for understanding and generating complex code segments efficiently. If you found this useful, please give the video a like and consider subscribing for more AI and coding tutorials. Thanks for watching.